Good morning.
Great. Any questions? Do you people have any questions before I start off with one of the most important concepts that we need to learn because it directly pertains to the strength of the material, the title of the course. Any questions? Okay. If no questions, we started discussing about strength of a material, and that is directly related to how the material fails. Okay. So if I know the limit of limiting point where the failure starts to occur, or the onset of failure occurs, that's the point where we can define also as the strength of the material. Okay. So with this idea, we look at the failure of the material and see how we can connect to the strength of the material as such. All right. So we started discussing about those. I pulled a piece of chalk. I also used a pair of scissors. The one that I pulled was breaking in such a way that when the normal stress goes to a higher, a limiting value, the failure occurs. Similarly, when a pair of scissors is used, a pair of scissors is often not called pair of scissors, but a pair of scissors I would elect to call a pair of scissors as a shearing instrument or a device. Okay. So from now on, just ask for a shearing device. Okay, which is nothing but a pair of scissors. One of them is a pair of scissors. Yeah, shearing. Yeah, shearing device. Okay. It can be any of those where direct shear is applied in order to break or cut things. Okay, so we can call that as shearing instrument. Okay, so we looked at those and tried defining how or tried understanding how strength of the material could be obtained. So if you recollect, we had something like this where we plotted stress versus normal stress versus shear stress. Okay. The first question we asked is how do we now translate this into an equation form? What does the equation say? The equation perhaps has to say that when the stress, normal stress goes to a limit, so I'm going to call that as sigma f, then failure occurs. Or if I have to define this as a line over here or a curve over here, I'll say sigma minus sigma f is equal to 0. And that's going to be something like this. Sigma minus sigma f equals 0. And this point is the value sigma f. Okay. Mind you here, this is a stress, normal stress that is applied, whereas sigma f is the property of the material. So this defines the strength of the material. Okay. But not all materials fail in this way. Some of them we can use a pair of scissors, in which case we are applying a pure shear, to the piece of paper or metal or whatever, right? In order to get it to fail or to cut the material. Okay. And we concluded that okay, when the maximum shear goes to a limit. So I'm going to call that as critical. Okay. Then the failure occurs. Okay. Now tau max here has to do with tau, right? So what we are now talking about is something that goes this way. This is tau minus tau critical. I'm just going to say tau c is equal to 0. Okay. So we have two lines. One line is horizontal, the other is vertical. Both define, depending on the material, they define the criteria for the material to fail. Okay. This kind of material which shears is a material that is often a ductile material, whereas these materials that break are brittle materials. So this is in a way brittle, we use for brittle materials, whereas this in a way we use for ductile materials. This is what we discussed last time. But if you ask me, is this how all the materials behave? The answer is no. These probably are sort of limits by which the materials behave. So in between is what we should be looking at as almost all the real materials. Okay. Now, before going further into all those, let me also introduce something. We looked at this example, and there is a plane here, and when I apply a load over here, this is going to slide along the weak plane. And if there are numerous weak planes, then it is possible to define tau max, right? Now, in this, I made an assumption that the normal stress that is applied like this, the normal stress that is applied like this does not have any role to play in terms of the resistance to motion. Okay. When does it occur? When does the resistance to motion becomes larger? When the normal stress is higher. In what kind of situation? On the chat box. When the normal stress is higher, the resistance to motion, when there is friction. Fantastic, right? So we can now think of friction. Okay, that we know of is that, let's say, is dry friction. In the case of dry friction, I have a block. I have a, let's say, compressive stress. So I'm going to call it as minus sigma, right? And let's say I'm trying to push this block. This is through a shear force. The reason why I'm saying shear force is it is horizontal. It is along the horizontal or along the plane of movement. Okay, and there is resistance over here. Okay, I know that the resistance is going to change as the normal stress changes in such a way that at the critical limit, tau goes to a value which is equal to minus tan phi sigma. This minus indicates compression, compressive stress. This is the tau value. When it reaches this, the failure starts to occur, or the sliding starts to occur. Okay, so we introduce this into this formulation. How do we introduce? That's very simple. All I have to do is just draw this equation. At sigma is equal to 0, tau is equal to 0. So we have to start from here. Right? Nothing is available in the positive zone. It is only in the negative zone. We have something like this. Okay. Now the question is this tau plus? Does it matter if the tau is positive or negative? The answer is no. And therefore, I'll introduce an absolute value over here. So if I introduce absolute value, then it is going to become something like this, both at positive and negative. This is, let me call it as, right, yeah. This is phi, this is phi. Okay. This is angular friction. Now, if the stress state falls within the zone, then there is no failure. Or in other words, this is the failure envelope that I can define for a material that behaves like this. Since it is to do with friction, we can call this, first let me write the equation. This is tau is equal to tan phi times minus sigma. Okay. And this is for frictional materials. Often you would have seen sand piles with an angle of repose. That angle of repose is connected to the friction that it offers, beyond which it starts to slide. Right? So far, so good. Any questions on this? Any questions on this understanding? Remember, we are drawing the envelope. This is one envelope that we drew, which is tau is equal to tau c. This is another envelope that we drew. And then the third understanding or idea had to do with the frictional materials. What's the difference between this and this? This is inclined, this is straight. The other important thing is this is tau minus tau c is equal to 0. Now, we call this kind of friction. I'm going to call this as friction. This kind of friction as a viscous friction. Okay. Or in other words, if this is dry friction, this is wet friction. Okay. In any real material, it is possible that we have both of them participating, not necessarily only frictional or only only dry frictional or only wet frictional. Both will participate. So far, good. Is understanding okay? Let me draw it again. Don't have any questions on this. So this is stress. I'm sorry, I should have made this as tau, because that's the convention that we used. So this is tau. What we had for a frictional material is like this, and this was for cohesive material or material with constant tau critical. Are you able to see this? Are you able to see this? Okay. Now, this is an equation which says tau is equal to minus, shall I call this as mu, coefficient of friction, mu, in which case this is minus mu sigma. And this is tau. Remember, I'm using absolute value here because this line and there could be one more line over here, right? This is equal to tau c. Okay. This is a positive value of tau c. And you have minus mu sigma here. Now, it is neither this nor that, but a combination of these two. So one idea that you could have is, let me combine them and write it this way. One due to the wet friction or cohesion, and the other due to the friction on the surface. Okay. And this negative is just to make sure that we are looking at a compressive stress rather than a tensile stress. Okay. This makes it more general compared to either looking at this or the dry friction. Okay. So if I have to draw that, I can erase these and I can draw. If you look at this, if sigma is equal to 0, tau is equal to tau c, which means that I have one value here, which is equal to tau c, right? And it is now in the decreasing with sigma, so which means and it's also a straight line, I'll get it to be something like this. Okay. Beyond this, it is equal to 0. Okay. It cannot take any load at all. Okay. Within that, this is phi. Within this is the region where I'm safe to apply the stress and the material is intact. Okay. Very simple idea. This was due to since we are using frictional material, it is Coulomb, and the idea that it can be a curve like this came from Moore. So this is called Moore-Coulomb criteria. Okay, named after the two people. Okay, but I would not want to use names over here. So we will call this as wet cum dry friction criteria. Okay, better to avoid names because there will always be some controversy. Oh, okay, it is not Moore, it's somebody else who preceded that proposal of Moore, etc., etc. So I don't want to go into all those details. Instead of saying Moore-Coulomb, we can say wet, dry, frictional criteria. So far, so good. Any questions? Any questions? So we looking at simple ideas. A more general possibility could be, why should it be a straight line? It can also be something like this, where I could have tau is equal to some function of the normal stress. And this is the most general possible failure envelope that I could have. Okay. All right. Let's look at this more specifically because we had some physical understanding over here. Whereas this is something that is very, very general, may not have the physical connection to it, but this seems to have physical connection. If I have something like this, there is an effect due to normal stress. Also, I'm considering sliding. While it is sliding, it is also the bonding between the two surfaces that will matter, which come in as tau c. Okay. So in that sense, this seems to be more general, physically acceptable failure envelope. Why am I using this word fail envelope? Why am I using that word envelope? Any questions? Any reasons? Why is it that I'm calling that as envelope? Why am I calling it as envelope? No answer. Why am I calling this as an envelope? What does an envelope do? Encloses something. What does it enclose? Safe area. Fantastic. Thanks, Mohammed. One thing that you can realize here is any Moore circle that cuts, let's say, that cuts the envelope automatically is an unsafe Moore circle. One may ask, sir, these points are remaining inside. But remember, this entire circle has to do with one single stress state. All right. It's a means of understanding that we have drawn this circle. So anytime the circle crosses the envelope, it means that stress state is that of a failed stress state or stress state which is not safe. Okay. So in that sense, if I have to have If I have to have these stress states, it could be a circle enclosed like this, or it could be a circle which is completely within. This is the limiting circle, right? If I have a limiting circle here, it may be larger. As I go further down into the compression, it will become larger and larger, right? Another thing to notice is, shall I erase these? It's a very small board, so I'm finding it difficult to completely write down everything. In a classroom, that would be easier because we will have multiple boards. All right. Now let's look at this again and ask a few questions. Okay. Can I reproduce tau is equal to tau c, which we started with earlier, from this equation? Tau is equal to tau c. Can I get from this equation? Just put sigma equal to 0, but sigma equal to 0 is something that I apply. For what kind of materials will tau is equal to tau c be valid? Mu equal to 0, right? So if I put mu is equal to 0, then I get back this, which was proposed by Tresca, right? How about this? Minus mu sigma. This is simple. If I take tau c is equal to 0. So this is ductile. Okay. I'm saying ductile material, but most metals behave like this. So ductile metals. Okay. And this is that of purely frictional materials. All right. Yeah. So far, okay. Any questions on this? So we have purely frictional. We also had one more, which was we had sigma is equal to sigma f. How do we get this? What do we do to get this? Remember, this is for brittle materials, right? How do we get this? Quickly. How do we get this? Sigma is equal to sigma f from that equation. Folks, you're slow today. I need to get sigma is equal to sigma f out of this kind of equation. What should I do? Okay, so let me ask this question. Is tau z equal to 0? Should tau c be equal to 0? Yes, okay. Then, instead of looking at all this, go ahead, look at the stress of space. How was it? It was like this, correct? It was like this, which means that tau c anyway is equal to 0. But also, you have mu should be equal to mu, or the angle of friction should be equal to 1. 1 means sigma. There was no tau there. There is no shearing. It is only separation. And therefore, I will also have this angle to be 90 degrees. So phi becomes pi by 2. Then the extreme case of sigma is equal to, so basically if I had something like this, now this angle has now become 90 degrees. So when I have tau c equal to 0 and pi is equal to pi by 2, then I can get the criterion for brittle materials. Okay. But most real materials, I would go with this kind of a thing. Okay. Another essential difference that you notice is supposing I look at this, there is this material property, correct? This is that of the material property. This is the actual stress that is being applied, right? Here, this is the material property. This is the actual, this is related to the actual stress that is applied. Here, this is the material property. This is the actual stress that is applied. Or in other words, is related to the actual stress that is applied. Okay. So in all the three here, there is only one constant that I need to find out, a single constant. Is it not? Right? Whereas if you look at this as this and this two constants to be found out. Right? And what are these? These are material properties or parameters, material parameters. For each material, I should be able to table these two. In this case, I should be able to table one single value for the as material property given a particular material. Okay. And this is the idea that we will go with as far as strength of the material is concerned. Okay. Of course, as you saw earlier, the most general one would be tau is equal to a function of normal stress, right? But this is too general and also phenomenological compared to some physical understanding that we have as far as this is concerned. So I would urge that we go with this kind of a thing unless there is some scenario where this does not fit in. Okay. All right. Now, how do I find out these constants? How do I find out those constants? I'm given a material, let's say this piece of chalk. How do I find out that constant? Go ahead, answer on chat box. How do I find out those constants? How do I find out those constants? Is my question clear? Because many of you are not answering. For those three criteria, tau is equal to tau c, or sigma is equal to sigma f, or tau is equal to minus mu sigma. In all these, one single material parameters needs to be found out. How will I be able to do find out that material property? What should I do? On the chat box. How come today seems to be very dry day? Yeah, but graph is not going to give me anything, no? I need to find out the material property, right? All these are material parameters. These are material parameters. How do I find those material parameters? What should I do? How do I know when this breaks? Experimenting, right? I have to do a test, right? In the test, what I should do is I should apply a known stress state, right? And find out at what point of that known stress state will it break. For example, if I take, let's say, a simple rod of the material and I pull it, okay? Let's say this is the stress that I'm applying. I keep increasing the stress. So this is, let's say, some deflection and this is stress, okay? Now I keep increasing as I keep increasing, this goes up, and at a particular point, it gives way, right? And this point is the point of failure, right? Now, what is the stress state over here? The stress state here is sigma 0, 0, 0. If I assume this to be two-dimensional stress state, I have a sigma 0, 0, 0. Okay, and this is a stress state for which I'm trying to find out what would happen to this material. And I found that it is failing at sigma equal to sigma f. Okay. If you want to call it sigma f or sigma y, does not matter. Depends on whether it is a ductile material where we say it is yielding, or a brittle material where it is failing or breaking into two. Okay. Now I relate based on the equation. I'll relate, for example, if it is a brittle material, what we said was find out the maximum normal stress and equate that to sigma f. Okay. If I look at this sigma is already maximum normal stress, and therefore when I did this test and I found out this to be sigma f, then it's very easy. I just have to insert that and find out sigma f. Okay. On the other hand, let's say I'm not applying this. I'm applying a shear like this. Let us say a shear like this. Okay. Then what would happen? This would be 0 tau 0 as the stress state. Listen to me carefully. This is the stress state. Now I asked the question, at what value of the shear will the breaking occurs? So I do the experiment and I find that at tau f, failure occurs. But I need to relate it to something like this, right? So I'll ask that question. What is the maximum normal stress due to this stress state, so that I can now use that information and write it here. Okay. So how do I do that? That's not difficult for me. So let me draw the Mohr circle for this. Tau sigma, right? And for this, Mohr circle would be what? It will look like this. It will look like this. Am I right? Yes or no? It will look like this. This is at the center. Yeah. Now, as I keep increasing, this circle is going to become larger and larger. And at a particular point, let's say tau f, the failure occurs. Okay. If you notice, on the horizontal axis, this is sigma 1 and this is sigma 2, the two principal stress points. And at this plane, at this, let's say, angle, whatever be the angle with respect to this, there is only normal stress and is equal to sigma 1. Okay. And the question that we are asking is, at what maximum normal stress is it breaking, right, for the brittle material? So I will find out sigma 1, which will be a function of this tau f. In this case, it's very simple. It is equal to tau f. If you notice this circle, this is the radius, this is the radius, which means sigma 1 is equal to tau f. So now it's very simple. I'll write this as, for the material that I experimented, sigma x is equal to tau f. Depending on whether I'm doing a tension test or a shear test, I'll be able to get a value of the shear or the tension where the failure occurs, and I'll insert that as the material parameter over here. And therefore, I have an equation that tells me what happens, whether the stress state is such that a failure occurs or not. So far, so good. Any questions? Now let's turn to one more example. Let's say instead of brittle material, I'm now going to focus on ductile material. Okay, so purely ductile material. I know Tresca condition can be applied, which is nothing but tau is equal to tau C. When tau reaches tau C, so this is the failure condition. This is the failure condition. So let me do the same thing over here. The simplest test that I can conduct is a tension test. So I apply sigma over here. Okay. I can draw the Mohr circle for this. Anybody who can help me with the Mohr circle? Where will the center of this Mohr circle be? Since you're doing the assignment, I can ask this question now. Where will the center of this Mohr circle for this? Origin. Where will be the center of the Mohr circle? On the sigma axis. Fantastic. One is on the sigma axis. What else can I gather from this? What else can I gather from this? I know that the sigma 2, if this is sigma 1, this is sigma 2 is equal to 0, and this is sigma. So one of the points is on this, the other is on sigma, right? That's a sigma. Let's say this is to failure, so I'm going to put it as sigma f or sigma y. Okay, so this is sigma y. So the circle that I can draw will be something like this. Yeah, yeah, and therefore the center is at sigma y by 2. Okay, we can get the radius. Now it is also possible for me to find out what would be this. If I call this as tau minus tau c is equal to 0, then I can find out tau c. Tau c is nothing but sigma y by 2. So now I can substitute saying that this is sigma y by 2. What did I do? I did an experiment and found out sigma y. Okay, or 2 tau is equal to sigma y. This is the condition now. Now this is tau, which is the maximum shear that I can find out. If you look at this carefully, that's how it is. Now, I'm going to now offer 2 marks for an answer from you. Okay. If the Mohr circle, listen to me carefully. If the Mohr circle has shifted somewhere else here as the center, if the Mohr circle that I draw for a particular state of stress, the center is over here. The radius remains the same. The radius remains the same. But the center has now, because of the stress state, has moved to another point over here. What will change in this? Is the question clear? I did the tension test and found out what this tau c is. Now I asked that question, oh, okay, now I have a stress state whose radius, whose Mohr circle has the same radius as this, which is sigma y 2, but the center has moved somewhere else. What's your observation on that? Doesn't matter whether it is positive or negative. I may have it over here or here or here. Doesn't matter. There is something that I observe as far as this ductile material failure is concerned. What is that? Remember, this is a different stress state. We put a circle over here. This is a different stress state. This is a different stress state. Okay. And let's say the radius remains the same of the Mohr circle. What do I conclude for those stress states? So this is stress state 1, this is stress state 2. Let's say I'm going to make it more clear. This is stress state 3. This is with the center here. There is a stress state 3. Okay. For these 3 stress states, this is 3. What is it that I find out? What is it that I find out? Quickly. Exactly. Who said that? Nishan. Fantastic. The magnitude of tensile stress. No, not tensile stress. Nishan is correct. Remains the same because of the same radius. What remains the same? Tau is independent. Not tau is independent. What is independent? Not tau, but tau c. Or in other words, all the three states, stress states that we have drawn, pertain to stress states at the onset of failure. Correct? So what I conclude from here is, as one of them said, it is independent of the center of the Mohr circle. And what does the center indicate? It is what is the center equal to? Center is equal to, do you remember? Sigma? Any of you? No, it's not sigma y. What is the center? How do I find out the center? Looks like many of you have not done the assignment. That's why this problem. The center is equal to the average of the two diagonal stresses. Okay, it is also equal to the sum of the half the sum of the principal stresses. Okay, supposing I have some situation like this, where it is sigma 1 here, sigma 2 here, there is no shear on this. Okay, supposing I move this center back and forth, the sigma 1 and sigma 2 will keep changing, right? And sigma 1 plus sigma 2 by 2 will keep changing. But what will not change is the radius. Correct? Or, in other words, any ductile material seems to be independent of this quantity, sigma x plus sigma y by 2. Are you able to understand? Immaterial of this value, sigma x plus sigma y by 2, the failure is completely dependent on the radius of the Mohr circle only. Got it? Okay. In a three-dimensional scenario, this translates to sigma x plus sigma y plus sigma z by 3. Okay. I'll come back to this point much later, but just have a flag on this so that we understand this notion of whether we move it this way or that way, it does not matter. For the ductile material, it remains the same. Okay. All right. So we did for ductile material, we did for brittle material. We can do a similar thing for frictional material also. But the fact of the matter here is I need two constants to be obtained. How do I obtain those two constants? Of course, experiments. But how many tests should I conduct to obtain the two constants? In these two, we conducted the ductile and brittle material, we conducted one test, tension test or the shear test. For this, there are two material constants, which means what? I should conduct two tests, right? So suggest two tests for me now. Suggest two tests. Come in. Suggest two tests for me. What did we do for ductile and brittle material? Doesn't matter brittle material or ductile material, we did a tension test. Fantastic. One of them is saying tensile test and a shear test, right? As long as these two are different stresses, it is perfectly all right. What is the other simpler one? Tensile test plus tension is pulling. What could be the other? Compression test. Fantastic. So I can do two of them. I'm going to close today's discussion on that. Let's say I do a tension test. Okay. The tension test is like this, right? You already know. And how does the Morse circle look like? The Morse circle has to have 1 as 0, right? Sigma 2 is equal to 0, sigma 1 is sigma, right? So it has to emanate and have a positive side circle as Morse circle. Is this clear to you? Is this understood? Yeah, because one of the principal stresses is 0. I can do the same thing for compression, right? This is compression, which means it should be in the other side. Again, the sigma 2 is equal to 0, which means I should have some circle of this sort. Okay. And what did we say? Uh, this to be an envelope, which means what? I should have an envelope that covers barely these test states, right? And this is the envelope that tells me whether the material has failed or not. Okay. As you can see, if sigma is equal to 0, this is equal to tau c, which means this is tau c, and this can be found out from these two circles. Okay, by taking the perpendicular radius here, perpendicular radius here. The rest of it is geometry. You can find out phi, you can find out tau c from these two tests. Okay. As somebody pointed out, it can also be tension test and shear test. So let's do that also over here. Okay. Any questions on this? Is this clear? Yeah. So it is possible for me to do, but I should do two tests. One is a tension test, the other is a compression test. One of the suggestions made by Mohammed is this. No, you do tension test, but do a shear test. So Mohammed, tell me, how do I draw the shear test state here? Yes. How do I draw the uh, shear test here? Mohammed, I want to draw the Mohr circle of the shear test quickly. Anybody else? Doesn't matter. I conduct a shear test. It is a circle around origin. Fantastic, fantastic. So basically, I will have something like this. Don't mind my assume this is a circle, okay? So the center is origin. That circle also will touch here, which means that I have one circle that is touching the envelope, and the other circle from tension. So this is the tension test, and this is the shear test. You may ask, doesn't matter, can I do some other test? The answer is yes. Basically, what I should have is two different circles. That's all. Okay, whether it is compression test or tension test or a shear test or a combination of any of them, it does not matter. As long as I have two circles which are different from each other. Okay, I can't say, oh, okay, let me take one of them which is a tension test like this, and let me take something that is a shear test with certain let's say a shear test with certain shift in the origin. It does not give you two different constants, because I need to have two different constants. I need to have two different circles. As long as I maintain that, it is perfectly all right. Okay. So just to conclude, what matters here is the envelope. Okay. So whether it is like this or whether it is like this, where I just need to find out as the state, right? Or if it is like this, where again I draw a Mohr circle, and if the right hand side of the Mohr circle touches this, then it is for brittle material. Mind you, for brittle material alone, it is only the tension that is responsible. So if I do a compression test, I will not get anything that is meaningful, because the compression test will give me a circle which is the compression side of sigma. I need to have some tension side that is available as far as circle is concerned. Okay. So based on that, I'll be able to evaluate whether the material has failed or not. So a stress state that will give me a failure mode is what I should have in the experiment. Okay. Any questions? Any questions so far? Okay. So basically what do we do? If it is single material constant, apply a known stress state where you can increase the magnitude of the stress, right? As you increase the magnitude of stress, at a particular point of the application of stress, it fails. Failing could be yielding or a separation, right? Or a combination of the two. But if it is just a separation or a sliding or yielding, then I'll find out what the stress state is, draw the Morse circle, and find out where it hits this if it is a ductile material, where it hits this if it is a brittle material, so that I can find out the material constant that pertains to each of this material. If it is a general material, I'll conduct at least two tests, physically meaningful envelope if I have to have. I'll conduct two tests and draw this. If the material is such that if I did one more and that happened to be something which is not touching at all, or perhaps this is the failure state for the third, what should I do? This is number one, number two experiment. This is number one experiment. Number three experiment where failure occurred for this circuit. What should I do? You understood the question? I conducted two tests. I got this. Third test I conducted, but the circle seems to be such that it is not tangential. The envelope is far beyond the circle that I have for failure. So what shall I do in such a scenario? Okay. No, I have, see, this is the failed state. This is a failed state. This is a failed state, this is a failed state, and this is a failed state. But this circle is not touching the envelope of the Mohr Coulomb. So what should I do? I should say that this is not valid. Let me go for a more general criteria so that I can now have an envelope which is something like this, which is like this. I can now have an envelope that connects all these tangential points. Got it? And that's the more general one, which is Mohr's envelope. Again, I don't want to use Mohr's here, so it is general envelope. Got it? Is this clear to you? We touched upon one of the most important concepts in strength of materials, which is to do with how do I connect strength of the material with the stress states that I have. Okay. That's why we did all the transformation of stresses, etc., so that we get a clear picture of when this material would fail, at what stress state the material would fail. Okay. Any questions? Any questions you may have? Any questions? No questions? Okay. So that completes how we relate stress with strength. Okay. Later on, we'll come back. So general equation is, yeah. So basically, if I conducted many tests and this kind of discrepancy occurred as far as this is concerned, then I'll say, oh, okay, let me put all those Mohr circles for which I have done the experiment, and have the envelope in such a way that it covers all the circles of the stress states for which failure occurred. Okay. So that's the general equation that I'll use. Tau is equal to f of sigma. Okay. And I'll find out what that curve is by a simple curve fit. Okay. After all, what we did here is in a way curve fit, except it is a straight line. Okay. Good. If you ask me where this material would be available, it's very difficult for me to say. But general set of materials books cover almost all of them, but not in a sense that we have discussed. Okay. So look up that way. Thank you. Do we have this in the lab? Yes, you have it in the lab. Okay. In fact, I wanted to have lab conducted in such a way that you do the experiment at home, but it has not been agreed to. So we'll wait. Okay, folks, I'm already past time. Thank you. We'll meet tomorrow. Okay.